Hello?
Hello.
Hello.
All right. Okay, I need you to help me. Does this sound better audio-wise? Or does this sound better audio-wise?
Second one.
Is there a difference?
The second one's a little better.
That's all I want.
Yo, come here. Get in this class, dude.
Do we just want to call in from there if we have a link? That'd be smart. Yeah, let me see.
Someone's gotta connect their computer, I think.
Or we just connect the other. Yeah.
Okay, so today we're going to be we're going to skip one lecture ahead because the MetaMask stuff we're actually okay. Yep, today we're going to skip one lecture ahead because what was originally planned for today, I think it's better to do it in person. So let's see. Okay. Before we get started, is there any news that anyone wants to share? Anything noteworthy besides the shooting that's happened a couple days ago? Any crypto news? Okay, we have nothing. That's fine. Not very eventful. Bitcoin's going sideways. The market isn't doing much. No crazy pumps. No liquidations either. So let's start off with a bit of review. Okay. And you'll see me do this over and over again. Okay. Because I really want to hammer those concepts into your head. Okay. So let's kind of look back. All right. What we talked about a couple of lectures ago. Okay. So who here wants to give a brief recap of like what is a UTXO and what is an account system, and how why does Ethereum use an account system and not UTXOs?
I could go. UTXOs are used in Bitcoin. The way they work is whenever Bitcoin transactions are sent, UTXOs are collected, and then they're destroyed, and then new ones are created to be sent to the individual wallets as well as change wallets. They do this to prevent double spending. And Ethereum uses an account system to prevent double spending. They use count nonces, which count up and not down. And the reason why they use this system rather than a UTXO is because there's a lot more information and data that Ethereum transacts rather than just like Ethereum transactions. There's also smart contracts that are living on the blockchain.
Yep, that's a great answer, right? So on the Bitcoin network, it makes sense to use the UTXO system because on one hand, it innately prevents double spend because as Richard said, things get destroyed, right? The input of a transaction gets destroyed with the transaction and new ones are created. So you can't really use the same input twice because it's not going to be there after the first transaction. But Bitcoin is just again a peer-to-peer electronic cash thing. It's rather simple. The only thing that you have to keep track of is how much money anyone has, right? But on Ethereum, things are a lot more complicated because now we have programs, we have smart contracts, right? And they have contract storage, right? Which represents the data that are stored within the smart contracts, right? We also have contract code, which represents the logic. And users, or not users, but users on Ethereum, they can submit a transaction, interact with a smart contract, and actually modify the contract storage based on the logic or what the contract code actually is. So the system is a lot more complicated, right? And and this is why Ethereum needs to keep track of state explicitly, because otherwise, if everything has to be calculated on the fly, then it's way too much computation for any client. It's going to be too slow for anyone to just get caught up on everything, right? Not to mention, and you still haven't even done the interaction, right? So that's the main problem. Okay. Also, yes, we on Ethereum we use nonce to prevent double spending, right? So every account has its own nonce, and every transaction also has a nonce. The transaction nonce must be greater than or equal to the account nonce, right? If it's less than the account nonce, then the transaction is considered outdated, expired, and it won't be. It will basically be thrown away by the nodes from the mempool. All right, and the account nonce increases by 1 with every single transaction. Okay, which means you can't copy and paste the same transaction, and then because Ethereum doesn't have the UTXO system, right? So if I'm sending John 10 ETH and I have 100 ETH, without the transaction nonce, John can probably just copy and paste it a bunch of times, right? And just keep broadcasting the same transaction unless I don't have any more balance left. Because there's nothing, because my 10 ETH, because it's just a number, it's just a subtraction thing, right? You're just taking 10 ETH from my balance, right? You can keep taking it until I run out of balance, right? Unlike Bitcoin, where each input is like a discrete thing called an UTXO, and if it's destroyed, then you can't spend it again, right? And Ethereum uses a nonce where basically after the first transaction goes through of me sending John 10 ETH, my account nonce will be increased by 1. And if John tries to replay the same transaction again, the transaction nonce will then be lower than my account nonce, right? So the transaction will no longer be valid. Okay, so that's the important thing about nonce. And we can also use the same principles to trick the system, right? To cancel a stuck trending transaction. Okay, if the transaction's gas price is too low and no miner wants to pick it up, then if you want to override it or cancel it or do whatever, you can just send another transaction with the same nonce but higher gas price. Okay, so the miners will process that one first, and then when they finally get to the one that was stuck, they will see that the nonce is no longer valid. They just throw out the transaction. Okay. All right, so that's the important part. So let's now move on to this part. Okay. Okay, who here remembers what is not what is an EVM? Yeah, who here remembers what an EVM is? What a VM is? What's a virtual machine? Just, you don't have to be 100% correct. I know it's being recorded. I mean, everything's being recorded, but it's okay. We'll keep this a secret, right? No penalties given for wrong answers. It's totally fine to be wrong in class. Yeah, so what is a virtual machine, or what is the Ethereum virtual machine in your own words? Nice, I've got a camera in the classroom. Thank you. No, sorry, go ahead.
Yeah, so Ethereum virtual machine basically just creates like an identical environment on every single computer, regardless of hardware, that allows smart contracts to run on.
Yep, that's exactly right. So a virtual machine, what it does is that it creates a massive convenience for the programmers, because instead of having to write your program to run on all kinds of different hardware, like Mac or Windows or Linux or Android, whatever, right? If there's a VM, a virtual machine, then as a software developer, you only have to write your software once to run correctly on the VM. And the person or the entity who maintains the VM, they will figure out how to make the VM run on different systems. It basically shifts the bulk of the work that you have to do to adapt to different systems onto the authors of the VM instead of the software developers. Okay, and in Ethereum's case, right? Why do we need an EVM? Because there are a lot of different types of computers in the world, right? And there's Windows. There's actually Windows computers are a lot more prevalent than Apple computers, but not in Southern California, I guess. We just have like a lot more Apple stuff than Windows stuff. But in the world in general, Android phones and Windows computers are a lot more prevalent than Apple stuff. But as the let's say you're the Ethereum Foundation and you want, what if you told the Solidity developers they have to write different versions of the smart contract so that they can for it to be able to run on different Ethereum nodes, right? That just kind of that's not a great incentive for people. That doesn't encourage people to write anything. That encourages people to stay away, right? On the other hand, if you tell them just write it in one language and it's going to run anywhere, right? That was actually the premise of that was the promise that Java gave. If you've heard of Java, not the coffee, but the programming language, right? If you've heard of it before, then it was like the shit, right? In the 90s and the early 2000s, it was very popular. Or actually, who here has played who has played an online game on a web page that's written with Adobe Flash? I'm sure everyone, like most people, probably have played a game that's written in with Adobe Flash. Well, Adobe Flash, you can also think of it as some kind of a program that runs on some kind of VM, right? Only in this case, the VM is the Flash software and also the browser that runs on top of it, right? You only write a Flash game once, but it's going to run on all the browsers, and the browser companies will then worry about how to write the browser to code it in a way so that it runs on different different computer hardware, right? And again, so the point of having EVM is to make it easier for actual software development to happen on Ethereum in the Ethereum ecosystem, right? So we only have to worry about the software logic. We don't have to worry about how to make it run on different computers, because that concern should be a concern that the Ethereum Foundation or the core dev team should handle. All right. Who here remembers what is a bytecode? Or what it looks like too? Doesn't matter.
bytecode is just like a bunch of like random characters that isn't readable by humans, but it's readable by the computers.
Yep, that's exactly right. You know, it's the shit that rains down the matrix computer monitors, right? Which actually, you know, is totally false, because if you're really reading the computer stream or whatever, it should be binary. I don't know why they have like Japanese characters flowing down. That's just like that's just fake, man. Um, but yeah, bytecode is basically a kind of intermediate language that only the computer can understand. All right, it's not, so last time I didn't mention this, but there's another thing called machine code. Now, machine code is purely in binary, zeros and ones. Machine code runs directly on the device's CPUs, processing units, processors, all right? Like Intel or Intel Core or Apple Silicon or Qualcomm Snapdragon, whatever, all right? Bytecode is the kind of code that runs on virtual machines. All right, and then the virtual machine, the underlying virtual machine will then translate the bytecode into machine code, depending on which platform, which processor is, what hardware the VM's running on. It translates things differently. But at the end of the day, neither the machine code nor the bytecode is human readable. All right, we clicked into the link last time. We just saw a bunch of random numbers, right? Whereas, you know, if you looked at the Solidity source code, it was English. Maybe you didn't know how the syntax worked exactly, but it was English. You know, you could read words like contract or string. You know what a string is, like a uint, or stands for unsigned integer, which we'll cover today, right? At least it's somewhat readable. But then the bytecode, we look at it, it's just a bunch of random numbers. All right. So the bytecode again is, so if you think of the Solidity source code as some kind of instruction that both the humans and computers can understand, then the bytecode is purely for computers, right? Humans cannot understand bytecode, no matter how hard or you know, no matter how well trained you are. There's no way any human being can read bytecode. Like in the Matrix, you can't just stare at a monitor that flows like random Japanese characters and say operator. They're on the highway, whatever, right? Whatever they do in a movie. That's just not possible. Okay. Okay. So that was bytecode and that was EVM. And if you have any questions, stop me anytime. Okay. I'm going pretty fast for the review, but then the point of the review is, you know, to solidify any knowledge we covered in the past lectures. Okay. And also, when you deploy a smart contract onto the blockchain, it's a special kind of transaction, okay? It's a transaction that's being sent to the 0th address, okay? But the data that's contained within the transaction, the network will recognize that you're trying to create a new smart contract, okay? So the to field you can see here, it just says contract whatever created. But really, if you look at the transaction, it's actually sent to the 0th address, because the contract hasn't been created yet. You're not interacting with anything. You're really interacting with the network, telling the network, okay, I'm going to create a new contract, okay? And after this, if you want to interact with the smart contract, then the to address will be the smart contract address that you just created, right? Okay. So, and again, I'm not saying, like, let's say you deploy the smart contract and the smart contract has a certain address. I'm not saying it's impossible for it to have I'm not saying it's impossible for there to exist a private key that will correspond to the address of the smart contract. I'm just saying the address of the smart contract isn't generated from a private key. Okay, so going in reverse is impossible. Okay, but statistically, it is possible that some private key will correspond to that address. But before that happens, right? And this is like extremely unlikely. By extremely unlikely, I mean it's never happened before. Okay, and and before that happens, okay, the smart contract is basically owned by nobody. Okay, by default, it's owned by nobody. Later on, when we get to the midterm, you'll see that how you're able to ask the contract creator impose certain access controls onto the smart contract so that you or a certain number of people, specified addresses, can have more specific control over certain aspects of the smart contract logic. Okay, but by default, the smart contract is owned by nobody, meaning that if you send the smart contract some money, if you don't go through the logic that allows you to take the money out, then there's no way for anyone to just transfer the money away. Okay, and not even the contract creator. Okay, so this is why smart contracts are trustless. Okay, well, so first they're only trustless if the smart contract source code has been verified, meaning that the source code is public on Etherscan. That way you'll know for sure like what exactly the contract's doing. Okay, and then it's only trustless if you don't impose any control mechanisms over it. Okay, if you do have control mechanisms over the smart contract, it's like you have a safe, right? Not a safe, but it's like you if you live in an apartment, which is probably most of you. All right. If you live in an apartment with like a key or something, right? Sure, like only you can open your door, but guess who else can, right? The RA or the building manager can probably also open your door. They have like a spare key, right? And that's built into modern apartment communities. Like the management always has a spare key to just override your keys or whatever to get into your apartment. So that's not really a trusted situation, although no one else besides you can open it. But really, it's no one else besides you and also the owner of the building, right? So you can think of it that way. A truly trusted smart contract is like a building with no owner. It's like when you buy your own house, right? No one but you has the keys, right? Deletion is also possible, but and there's an opcode called self-destruct, but just a reminder, you can't truly delete something from the blockchain, right? Because you can always just look at the block before it was deleted and still see all the data that used to be present. Okay. All right, and we can skip over all of this. This is not too important. Okay. All right, so with that out of the way, the review stuff, and also again, stop me anytime if you have questions. All right. Let's get into what we're going to talk about today, which is some real shit. All right, it's going down today. Today we'll be talking about programming fundamentals. All right. Now this is not the best lecture to do remotely because it's pretty heavy. Okay, but luckily this is recorded, and also I'll be there on Thursday. So if you have any questions, we can talk about it or go over parts of it or whatever. I'm going to go over this pretty slowly. Okay, and you're going to catch me repeating shit every single week after week, coming back to a certain slide in this presentation. That's totally fine, right? Because in reality, programming should be taught in its own dedicated class. Okay, but here we're doing everything in one class, which means you have to give me 100% of your attention. Otherwise, like it's very, 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 very easy for you to get lost. Okay, but if you get lost, don't worry. Speak up. Just tell me that like you missed something. Like I can go back really quickly. Not a problem. Okay, just don't let it snowball. Or you can also, if you're too shy, if you're a shy person like me, I'm probably the shyest person in the room, right? Then you can come to me after class or email me, right? About what you missed or what you're confused about, or you can go to the office hours for TAs, right? They can also answer your questions, right? But whatever you do, don't let it snowball, okay? I sound like a broken record. Okay. One of my professors, I forgot if I mentioned this, he would say I sound like a broken MP3 player, but the problem is a broken record would play. It would just play repeatedly. A broken MP3 player wouldn't play at all. So it's like it's a poor attempt at being funny. Anyhow, okay, so programming fundamentals today, okay? So what is programming, really, okay? Programming is basically writing an essay, or it's not an essay, I would say writing some kind of manual that both humans and machines understand. And it's a manual for humans to tell machines exactly what to do, okay? So every single program has a purpose, all right? if your program has no purpose, then really it shouldn't exist. Because every single program should be written in order to accomplish something. Okay. A calculator program serves to do calculations, right? Facebook serves to sell your data, something like that, right? Okay, so today we're going to cover two concepts, all right? We're going to cover variables and functions. Now, if we don't finish, don't worry about it, okay? And if you're confused, if I use the wrong analogy, then, and if you don't understand what I'm saying, just speak up right away, okay? Or you can raise your hands and I can call your name, whatever works. But the point is, stop me, again, stop me if you're confused, okay? So, and also variables and functions, they exist across all programming languages, okay? So after we do this speed run of learning what programming is, like you're able to apply those concepts to other programming languages, no problem, okay? But this is also a challenge for me personally, because this shit usually you spend a whole semester on it, okay? But you know, we're not patient, right? In crypto, we're not patient. We can't wait to FOMO in whenever it pumps. Okay, variables. What a variable is really, it's something that you define in order to store some information into. Okay, so think of a variable as, I have it here, a wallet. Okay, how about not a wallet, just a card holder. Okay, now, so think of a variable as a card holder, right? Such a nice card holder. I wonder whose it is. Okay. And each variable, right, it basically has a name. So imagine this card holder having a sticker in front that says its name, and it can hold some information. Okay, in this case, it holds a Coinbase debit card. Okay. Now, in languages like Solidity, it's what's considered as a strongly typed language, meaning that every single variable has a specific type. Now, the type basically means what kind of information it can hold, right? So let me ask you a question. And by the way, this is not a trick question. Like for real, anyone can answer. What does a card holder hold? If you can't answer me, I'd be concerned. What does a card holder hold?
Cards.
Cards, right? Can it hold a leftover burger?
No.
No, right. That's not a trick question. It can't. Okay. A card holder only holds cards. Okay. And this is the case for Solidity. Okay. So each variable has its own type. Type meaning what kind of stuff it can hold. Okay. So imagine this is a variable that's called, let's say the name is Jack's wallet. Okay. And the contents, the information that it stores is currently my Coinbase debit card. Okay. So in other languages, such as JavaScript, all right, it's what's called as, what's known as a weakly typed language. Okay, I'm not sure about the exact term. So basically what I'm saying is, okay, imagine this imagine this is not a card holder. Okay, imagine this is a variable that only holds numbers. Okay, in Solidity, when you add one number to another number, let's say you add 1 to 2, what do you get?
3.
Algebra, pre-algebra. Yes, 1 plus 2 equals 3, right? But in JavaScript, it doesn't have strong. It doesn't have explicit types, meaning that the 1 that I have in this wallet can either be a number or it could be a string. A string meaning that it's like it's like Jack. It's like an English phrase. Okay, a string. So what happens? Let's say it basically means it's a word. Okay. So let's say. So let me ask you, what happens when you add two words together? What happens when you add Jack and professor together? When you add the two words together, you get one word called Jack professor, right? That's what happens when you add two words together. You kind of concatenate them, right? So in JavaScript, if you add the string 1 to a number 2, you don't get the number 3. You get the string 1, 2. Okay, so that's the confusing part about languages that are not strongly typed, right? Because like you're never certain like what the hell is actually going to give you. But fortunately for us in Solidity, every single variable specifies the type. Okay, basically it specifies explicitly what kind of stuff it can hold. Okay, so let's say if I want to describe my grade, not my grade in English class, but like the grade that I'm getting in English language. Okay, so one sec. Justin says, if the input combines an integer and string, would the output be a string in Solidity? So in strongly typed languages, you cannot combine things that are not of the same type together. It will give you an error. In JavaScript, you can. And the behavior is sometimes ambiguous, which is why it's kind of sketch. But in strongly typed languages, you can't combine different things together, right? Like you can't say like, how can I, like if you, let's say you're cooking, okay? And I'm telling you, like, let's say you're cooking soup and the soup is a little bit bland, and I'll tell you, add some salt and pepper to the soup, right? And that's totally doable because salt and pepper and soup, they're all foods. You can add them together. But if I tell you, can you add your memory into the soup? Like it doesn't make sense, right? So in Solidity, it's the same thing. It doesn't allow you to combine things of different natures together. So just in your case, the code wouldn't even compile because the compiler will stop you from doing it. It will tell you that you can't add different types together. Okay. Okay. So if I want to describe my grade in English, in the English language, okay, I would say that, let's say my grade is like a percentage, okay? So I will say that my grade, and this is like a very verbose description. No one ever talks like this in real life, okay? But if I want to be really verbose and specific, I can say my grade, which is a non-negative integer because no one can ever have negative grades, okay? It's 70, okay? Right, so this is like the weird way to talk about what your grade is, like, okay, buddy, all right? But it does give you the information that you need, okay? And this is a correct description of what my grade is, right? So, and we can imagine this as a variable, right? The name is called my grade, okay? What is the type? The type is a non-negative integer. And what's the value? The value is 70, okay? So what's the name of this thing? What kind of data it holds, and what actually does it hold? Okay, so the three different aspects of a variable. Okay, so if I want to describe the same thing in Solidity, then I would say my grade. So this is the variable name. Okay, but so what's the type? A non-negative integer. Right now it's UNT256. So that represents a non-negative integer. And I'll explain to you exactly what this means later. But just know that this represents a non-negative integer. And what's the value? See, so this grade is equal to 70, meaning that the number 70 is assigned to this variable whose name is grade of type unsigned integer, non-negative integer. Okay. Does this part make sense for everyone? I might going a little bit too fast, but just let me know. Okay. I'll give everyone some time to type. I will have some zesty drink. Okay, no questions so far. Okay, let's proceed. All right. So let's break down this thing. Okay. So UNT256 grade equals 70. What does this actually mean? Okay. So what is UNT256? Okay. So UNT256, UINT means unsigned integer. Okay. U stands for unsigned. Integer stands for int stands for integer, and integer is, you know what it is. So unsigned means that it doesn't have a sign in front of it. Okay. Okay. So let me ask you a question. When you write a positive number, do you ever write a plus sign in front of it? I mean, you could, but do you? No, right? You don't write a plus sign. You don't say that, like, let's say you're watching a basketball game or a football game or a soccer game, whatever, right? You don't say like the score is +3 to +1. You just don't say that. Or you don't say the score is +3 to positive. You just say the score is 3 to 1, right? Like a normal person, okay? Not like a computer science professor, all right? So what unsigned basically means is that there's no sign in front of the number. So if you're a normal person and you're writing a number, what does it mean if you don't have a sign in front of the number? It means it's a positive number or it's a 0, right? Meaning that it's not negative, because you only write the negative sign. You only write a sign in front of the number when the number is negative, and the sign you write is like a negative sign. Okay, so unsigned again just means that it's a non-negative thing. Okay, an integer meaning it's an integer, and unsigned integer meaning it's a non-negative integer. Okay, does that make sense? And conversely, okay, is that the right word to use even? I don't know. Signed integer means that it could be positive and it could be negative. Okay, and in Solidity, if you just have int, then it's signed. If you have uint, then it's unsigned. Okay, so signed integer is not sint, it's just int. Okay, but if it's unsigned, you specify uint. All right. Now, 256. What does 256 mean? Okay, it means 256 bits. Okay, and who here wants to remind me what is a bit? And don't tell me it means a little. What is a bit?
A bit is like a 0 or a 1.
Yep, that's exactly right. So a bit is either a 0 or a 1. It represents a number in a binary number system. Okay, so let me ask you a question. Oh, I can actually draw. Okay, can you see my drawing? Yeah. Okay. Good. Very nice. All right. So let's say we have so what is a bit? A bit is either a 0 or a 1. Okay, so 2 bits. So these are 2 bits, 0 and 1. Okay, and did Chaz ever teach you guys how to convert binary to decimal? Yes. Okay, I'm just going to do it again in case. I have to quit this to close the chat box. How do I? Okay. I'm a boomer. Okay. Okay, those that are in class, does this blue show up okay on the screen? Okay, perfect. So let's say we have a binary number 1010. Okay. So what does this number, how do we translate this number to decimal? Okay. The way to do it, okay, is, let me rewrite this, 10. I'm using my track. This is probably the best drawing I've done in a while. Okay, so 1010. This is our binary number. Okay, the way we convert it into, yes, Justin, thank you. But let me walk through it step by step. So the way that we convert this into decimal is, so binary means base 2. Okay, means 0, 1. Like decimal, we go from 0 to 9, and then when we go to 10. Right, we add 1, and then we flip the original digit back to 0, right? Or we carry 1 over the carry, right? Whatever it's called. So in binary, the way we do it is so actually let me actually revert to this. Okay, so let's say I have a number of 42. Okay, or 420. How about that? 420. So this is a decimal number, 420. Okay. How do I get from 420 to the decimal version of 420? This is like a weird question to ask, right? But basically my question is, how do you break this down into individual terms, into different components, right? So decimal, so decimal, as we know, is base 10, right? So the way that we convert this, which is already a decimal, into a decimal number is this. So this is 10. So we start from 10 to the 0, okay? So it's 0 times 10 to the 0, and then 2 times 10 to the first, okay? And then 4 times 10 to the second, all right? It's very painful. It's harder than it looks. And then when we add them together, okay? So what is what is 10 to the 0th power? It's 1, right? 0 times 1 is 0. 10 to the first power is 10. 2 times 10, 20. 10 to the second power, 100. 4 times 100, 400. So 400 plus 20 is 420, right? So this is how we convert a decimal into a decimal, which is a bit counterintuitive because it already is decimal, right? But the reason I'm doing this is so that I can show you how binary works. Okay, so let me move this. Holy crap. All right, let me move this around. So let's now do a decimal thing. All right. So the thing we have 1 0, let's do 1011. 1011, okay. So binary meaning base 2, okay. So we look at what we did for 420 here, okay, and we imitate, okay. So because it's base 2 and so base 10, we do 2 to the whatever power, not 10 to the whatever power, okay. So the first digit 1 times 2 to the 0th power. Holy crap, that is horrible. Okay. Second digit 2 to the first power. Trackpad getting sticky here. Okay, plus. All right. Third digit 0. 0 times 2 to the second power. Okay. Oh my gosh. It's starting to not look like numbers because it's horrible. And then the fourth digit is 2 to the third, okay? Oh my gosh. Okay. So now we've imitated how we converted a decimal into a decimal, but now we're doing a binary into a decimal, okay? So what does it give us? 1 times 0 to the 0th power. 1 times 2 to the 0th power is, I need someone to just say it.
1.
1, okay, yep. Justin already has the answer, but I'll go through it still, okay. 1 times 2 to the first power is 2, all right. 0 times 2 to the second power is 0. 1 times 2 to the third power is 8, okay. So we have 8 plus 2 plus 1, and this eventually comes out to 11, okay. So this binary this binary number 1011 comes out to a decimal 11. Okay, does this make sense to everyone? Whoever's nodding in the classroom, I need to do it harder because I can't see. All right, I can barely see one person nodding. It's okay. All right, so this is the binary and decimal conversion. The reason why I covered this, okay, so let me clear everything on the screen here, or let me move it around. I'll still keep it. Oh my gosh. Okay, let's move. Oh, what the hell just happened? Okay, I'm gonna. This is okay. Okay. So let's say we have a 3-bit number, okay? And okay, so let's say we have a three decimal number, a 3-digit decimal number. What's the largest 3-digit decimal number that you can think of? It's not a trick question.
999.
Yes, 999. Okay. Why 999? Because 9 is the highest digit, right? And when you repeat that, so you get the highest number, obviously, right? What's the smallest 3-digit decimal number?
0.
Yes, well, yeah, because 000 is 0. Okay, so the biggest 3-digit decimal number is 999. Smallest is 0. So let me ask you, what is the biggest 3-digit binary number? You can give it to me in binary terms. So what's the biggest binary number? There are only 2 numbers, 0 or 1. So the biggest number is 1, right? So the biggest, well, you don't have to convert it, okay? But the biggest 3-digit binary number is 111. Am I right? In binary terms, 111. Okay. So 1, 1, 1. Okay. And the smallest number is 000, obviously. Right. So the reason why I'm saying this is that I'm trying to show you the number, the range of possible numbers for a given binary bit, I guess, bit size or whatever. Okay, so the number 111, when we convert it into decimal, okay, so it's 1 plus 2 plus 4, right? Because it's 2 to the 0 plus 2 to the first plus 2 to the second. 4 plus 2 plus 1, that's 7. Okay, now what is 7? 7 is also 2 to the third minus 1. Okay, so if I have a uint 3, then the largest number that I can represent would be 2 to the third minus 1. Okay, so if we apply it to uint 256, then the largest number that we can represent is 2 to the 256 minus 1. Okay, so the bit number here will tell us the range of numbers that this variable is able to express, is able to store. Okay. Now, let me ask you a question. Okay. So let me erase some of this. This is pretty handy, actually. Okay. So this is our biggest 3-digit binary number, right? What happens if we add 1 to it? So let's actually take a step back. Our biggest decimal number, 999, right? What happens when we add 1 to this number? It's not a trick question. What happens when we add 1 to 999?
Get 1,000.
It's 1,000, exactly. Yes, yes. It's not a trick question. All right. So this will become 1,000. Okay. But we have a problem because I told you we're only able to store 3 digits. Okay. So now we have something that's called an overflow, because if you only look at the 3 digits, then 999 plus 1 equals to 0, because there's an extra bit or extra digit in the front that we just can't keep track of because we have limited space. We only have 3 number slots. All right. So this is called an overflow. Okay. Overflow meaning that you've gone over the deep end. All right. And you've wrapped around into the back to the very beginning. Okay. So this is what's called an overflow. And an underflow works the same way, but only you've gone off the shallow end, right? It's like, because, Earth is flat and you've gone off the shallow end, right? And what you just end up on the other side, right? So if we are in like a 3-digit decimal system again, okay, and and we have 0 minus 1, okay, and let's say the numbers can only be positive, then what we're gonna get is actually 999, okay. So that's called an underflow. All right. So this is just relevant to the uint thing. right? Because again, uint, it can't represent negative numbers, okay? So what happens when you do when let's say if the grade is, so the grade is still 70. What if you do grade minus 71? Then the number you will get is actually the maximum value that uint 256 can represent, because it wraps around to the other side. Okay, and that's one of the dangers of doing math in Solidity. Okay, although it's been fixed in recent versions of the compiler, but in older versions, this is extremely susceptible. Okay, so that's all about decimals and underflows and overflows. Okay, any questions? Might have gone too quickly. Any questions so far? Okay, so why don't we just use something like uint 2560? Because the largest thing that you can go is 256. The smallest uint that you can have is in uint 8. And in between, you can only go in increments of 8 because of how the storage slots in memory that Solidity is, like the way that it's designed, you can only, it stores 8 bits at a time. So you can only go in 8-bit increments for the uint size. And the largest thing is 256, because what is 256 divided by 8 bits? It's, so 256 means 256 bits, all right? And 1 byte equals 8 bits. So 256 bits is 32 bytes, okay? And 32 bytes is the largest amount of storage that could be allocated to, it's a single slot basically in the storage map, in the storage structure of Solidity. So you can't go past it, okay? Yep. Okay, any questions, any more questions on this madness before I erase everything? No more questions. Okay, no problem. If you have any questions, you can come find me after class. Okay. Maybe not today because I'm not actually here. Okay, so let me clear everything. All right. Okay, so that was just the first uint part. Okay, but don't worry, again, overflow, underflow, it's a concept in every single programming language. Okay, so everything you learn in this lecture and the next lecture, or whatever lecture that we talk about programming fundamentals, most of it applies to every single language out there, okay? Or most languages out there. Okay, maybe not Python because it's a fake language, okay? Okay, so that's uint 256 taken care of, okay? And then we have grade, okay, so that's the name of the variable. You can name it whatever you want, okay? So like this wallet, this card holder, it doesn't have feelings, okay? I can put a sticker on it and write like, I can call it like a piece of crap. Like it's not gonna just refuse to work for me anymore. If I press this button, the card's still gonna pop up, okay? So variables don't care what kind of name you give them, okay? The name is strictly for your benefit, okay? Because let's say I have 10 card holders that hold different cards, right? Each card holder, let's say I group them by banks, okay? So I've got a Coinbase only card holder, I've got a Bank of America only card holder, and I've got a American Express only card holder, and I've got a fraudulent bank, also known as Wells Fargo card holder, okay? So let's say I have like a bunch of different card holders that represents different banks lying on my table, okay? The card holders themselves, it doesn't matter what kind of names I give them, they're still going to hold the cards for me. But in the future, if I want to find my Amex cards, right, then I have to look at the labels I made earlier, and and if I named them poorly, then it's only going to annoy my future self because now I can't find anything, right? If you name your variable AAAA, which is fine, right? No one's stopping you from doing it. The program's not going to care, okay? But in the future, if you try to refer to like, oh, which variable did I use to store this person's grades? Is it grade? Is it something intuitive like great? No, it's fucking a. Why do I do that, right? So the name of the variable, the compiler doesn't care about it, the computer doesn't care about it. It's only strictly for your benefits that you can refer to that information later on. Okay, so what I tell everyone is name it something intuitive. Okay, name it something so that later on when you want, like if you're writing a program and you have like a user profile system and you have someone's age, okay, you just say age. You just name the variable age. Okay, you don't say like seconds since existence or some weird stuff like that, right? Just use the most intuitive name. Okay, and also don't do a b b b b b. Like it might work for you in the moment, okay, but later on, or maybe just after 20 minutes, you'll forget like what the hell you've written. Okay, so again, use intuitive names. And Richard, yes, it is case, wait. I'm actually not sure if it's case sensitive. Let's actually take a look. That's a great question. Because I'm so used to, because there's a certain convention that you're supposed to use. I forgot if it's case sensitive. Let's see. Yes, so in Solidity, variable names are case sensitive, okay? And this might be different for different languages, okay? But in Solidity, it's case sensitive, right? Thanks for pointing that out. Okay, and now we have the variable name, we have the variable type, and now equal sign. What does the equal sign mean? Okay, the equal sign basically means it's what's called the assignment operator. Okay, you use it to assign a certain value to a certain variable. Okay, you always assign what's on the right side to what's on the left side. Okay, this is a bit different from math, because in math, what you do is you have some formula on the left side, okay, and you work that out, and then the right side are the results. But in programming, you already know what's on the right side. You're trying to store what's on the right side to what's on the left side. So in this case, you are telling the computer that there's a number this number is 70. Okay, but what you're trying to do here is you're trying to store this 70 number into the grade variable. Okay. And also you can, and whatever's on the right side, it doesn't have to be a concrete number. It could be a different variable, right? You can assign a variable's value to a different variable. That's totally fine, right? Let's say I have grade equals 70. So this grade now holds a value of 70. And later on, I can create another variable called grade 2. Okay, so a second grade variable. And I can say grade 2 equals grade. And now grade 2 will also have a value of 70. Okay. And you see 70 is the value that you want to assign to the left-hand side of the assignment operator. Okay. And in the very end, we have a semicolon or semicolon, whatever, right? So the semicolon basically tells the compiler that this is the end of this statement. Okay, it's like writing a period when you're writing English. Okay, and we all know how infuriating it is to come across a Reddit post with like no punctuations. It's like a paragraph with no commas, no periods. It's impossible to read, right? And just like that, right? For compilers, if you don't add semicolons, then the compiler doesn't know like where does every sentence end. Okay. This is again why Python's a fake language. I'm kidding. But in Python, you don't need semicolon. Just go to the next line and it will know that you finished your sentence. But here in Solidity, not exactly. Okay. So in Solidity, C++, Java, the bigger languages, except for Apple's Swift language, you need a semicolon to basically act as periods to end your sentence, so to speak. Okay, so don't forget to add it to the end of not every line but every statement, and you'll see what I mean later. Okay, because there are statements that span multiple lines. Okay. Okay. So we talked about a single grade variable. Okay, it's in uint, right? Uint 256. But what are the other types? Okay, so we have, besides the uint 256, and again, we have the different uints, right, from uint 8 all the way to uint 256. As long as the number is a multiple of 8, it is valid. Okay. We also have address. It is pretty self-explanatory. It just represents an Ethereum public address. Okay. A bytes 32. Okay, it represents a 32-byte word. Okay. Now, what other thing is also 32 bytes? A SHA-256, right? SHA-256, again, is 256 bits, 32 bytes. Ain't that a coincidence, right? Now, you can also use bytes 32 to represent strings that have fewer than 32 characters. That's also fine, but it has to be fewer than 32 characters. And also, it has to be, when I say 32 characters, I mean 32 alphabetical characters, all right, or Latin characters, or whatever, like English letter alphabet characters, or alphanumeric characters, I guess, right? If you start typing in Chinese or Korean characters, then you're not gonna be able to reach 32, because for those more complex Chinese or Korean or Russian characters, every single character is actually more than 1 byte. Okay. Okay, so we also have, besides address bytes 32, we also have Boolean. Okay, bool. Now a Boolean is basically either, it can only have, there are only 2 possible values for a Boolean, true or false. Okay, it's just a true or false. Okay, and internally, it's actually represented by uint 8, because if you think about it, right, true or false is really just 0 or 1. They're basically the same thing. Okay. But the smallest number that Solidity can represent is uint 8. So a Boolean underneath really is in uint 8. But but when you say Boolean, then I know your intent, right? It's like, no, I don't have a good analogy. But basically Boolean is true or false. Okay, represents true or false. Uint 256, we already covered it. Okay. And then we also have int 256. All right. Now, int 256, as we said earlier, right, it represents a signed integer, meaning that it could go negative. Okay. Now, because it could go negative, it needs a single bit to keep track of if it's positive or negative. Okay, so it sacrifices 1 bit to track the sign, if it's positive or negative, which means the range of numbers without the sign is actually cut in half, right? Because when we take 1 bit away, then we divide everything by 2, right? So without the sign, a signed integer can only represent half the number range compared to an unsigned integer. But because we have a sign in the front, so it's positive and negative. So really the range itself is the same, right? It's just the positive part is cut in half, but then you have like the negative part as well. Okay, so that's the difference between uint 256 and int 256. But really, like when you're using, like when the upper limit is like 2 to the 200 something power, then I don't think you'll ever run into a scenario where you're running out of digits to use. I just don't think that's possible. Like it's such an astronomical number. If you're just doing counting, it's never going to happen. Okay. We also have something called a mapping, which I'll explain later. It's actually quite complicated. It's probably one of the most complicated things that you'll have to learn quickly in this class. Okay, it's quite a brain twister for people that haven't learned programming yet. For people who have, it's just a dictionary. Okay, but for people who haven't, we'll walk through it in the next lecture or maybe the one after. Okay. There's also a string type. But what a string really is an array of bytes, okay? So remember how I said a bytes 32, you can use it to represent strings fewer than 32 characters. Well, what about a string that's longer than 32 characters, then you can just use a string type, right? So a string type does not have a limitation, okay? But it's slightly more expensive than using a bytes 32 because one, it doesn't fit nicely into one slot, right? When you have multiple, like let's say you have a well in your backyard, okay? And everyone here knows what a well is, right? And in order to get water from a well, there's like a bucket, there's like a pulley, and then you pull the rope, the bucket comes up, whatever, right? A bucket of water, okay? If your data fits into a single bucket, in Solidity's case, it's 32 bytes, then you only have to pull it up once, right? But if your data is in a string that's larger than 32 bytes, then you have to pull the bucket up multiple times to retrieve the whole thing, right? So not only is it, so string enables you to store more things, but potentially it also, it is also more expensive, not just because you're storing more things on the blockchain, but also when you're trying to retrieve that data, you have to send the bucket up and down multiple times to get the whole thing, okay? So that's the main difference between a string and a bytes 32, all right? And again, stop me anytime or type in the chat if you have any questions, okay? Okay, so we already went through this, right? We live in a society where numbers are indecimal, okay? We did the binary addition thing earlier with my horrible drawings, okay? We also went over this, right? Signed versus unsigned integer. Okay, this is just like in written form. You can, if my verbal explanation is a bit too confusing, you can also read my written explanation. Okay, so, but we've already gone through all this, right? So, and also this is what I mean by how int256 and uint256, they basically all represent this. They have this, so the range of numbers that they're able to represent is actually the same, okay? But if you only look at the positive part, okay, and unsigned can represent 0 to 7, but signed can only represent up to 0 to 3, okay? But because it's got a sign in front, it can also represent negative numbers that the positive unsigned version can't. So overall, the range is similar, except for the 0 part, because like there's -0 and +0. Okay, Benny, still a little bit confused with the numbers. Which part in particular? We talked about a lot of numbers.
Just like how to go from like 3 to 0, 1, 1. Or
Okay,
from
okay,
1, 1 to 3.
okay, cool. All right, so let's take a look. Do I have anything here? Okay. So let me draw it for the 0, 1, 1 case. Okay. So we have 0. Let's do 0, 1, 1 to 3 first, and we'll do 3 back to 0, 1, 1. Okay. So 0, 1, 1, right? So this is a binary system, meaning that we're using 2 as the base number. Okay. So on the very right side, we start from 2 to the 0th power, and then to the first to the second, as every digit, as we advance on every digit, we increase the exponent by 1. Okay. So this is 1 times 2 to the 0th power. Okay. Are you still with me on this part?
Yeah.
Okay. So that's the first digit, right? So now we move on to the second digit, and we increase the exponent by 1. So this is 1 times 2 to the first power.
So is the next one going to be 2 times 2 to the second power?
It'll be 2 to the second, but it'll be 0 times because it's 0, 1, 1.
Yeah. Okay.
So now we have 1 plus 2 plus 0.
I see. So that gets 3.
Yep. So that gives 3. Right.
So 0 for 0, 1, 0, you do 2 to the 0, 2 to the 1, and then 2 to the 0, and you just get to the 2 to the 1 is 2, and that's it.
Yep. Exactly. Yep.
So then how do you go from 3 to?
Yep. Okay. So from 3 to the other way around, we have to write out, actually, let me not erase everything. So it's kind of like doing division, but not really. Okay. So we have 3. Okay. Okay. So 2 to the second is 2 to the second power is 4. So 4 is larger than 3. Right. So we skip this one. 2 to the first power is smaller than 3. So we can write 1 here. Okay. So now instead of 3, we now have 1 left. And now we have 2 to the 0, which is 1, and 1 times 1 is 1. So this is how we get it. So let me use a bigger number to showcase this better. Okay. So let's do how about let's do 27. Okay. 27. So if we do 27, let's say, so we have to think of 2 to whatever power that's just bigger than 27. So 2 to the 4th is 16, 2 to the 5th is 32. Okay. So 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 to the 2nd, 2 to the 1st. Well, it's getting worse and worse. 2 to the 0. Okay. So first 27. So 2 to the 5th is 16 times 2. That's 32. So that's larger than 27, so we don't consider it, right? And then we move on to 2 to the 4th, which is 16. Okay. So 16 is smaller than 27. So we mark down 1. And let me move this. Oh my gosh. Okay. So 2 to the 4th against 16. And we wrote 1 down. Okay. Oh, damn it. So we do a minus 16. 27 minus 16 is 11. Right? It's 11. Okay, so now 2 to the 3rd is 8. 8 is smaller than 11. So we mark 8 down. 1. So 11 minus 8 is 3. Okay. 2 to the 2nd is 4. Okay. 4 is bigger than 3. The remainder 3. Okay. So we bypass it. Okay. 2 to the 1st is 2. Right. 2 is smaller than 3. So 3 minus 2 is 1. And then we mark 1 here. And 2 to the 0s is 1. Okay. So this just gives a 0 remainder now. And we mark 1 down. Okay. So 27 in binary form is 11011.
I see. Yeah, that makes sense on how to get it. So when do you
Yeah.
when would you have to when do you have to convert numbers into binary form?
You don't. I'm okay. So in more advanced use cases, there might come a point when you have to manipulate the bits manually. But that's not going to be in this class. That's not even true for most computer science people. I really just want to talk about the binary stuff to show you how overflow and underflow really worked. And this is just good to know in general.
Okay, sounds good.
Yep.
Thank you.
Okay. Yep. And also, why signed 111 is -3? Okay. So the reason signed 111, Richard is right. Okay. So the last digit, so it's actually the first digit. Okay. So 111, if it's signed, okay, then this one represents if it's positive or negative. Okay. So now you're really left with 2 bits to work with. So what's the biggest value for a 2-bit binary number? Is 2 to the 2nd minus 1, right? So that's the biggest number, that's the biggest value you can get, and that is 3. So that's why, right? Because 1 1 is 3, right? 2 to the 0 plus 2 to the 1st. 1 plus 2 is 3. Okay. Because the first bit, again, in the sign thing, it represents this positive or negative. So we can't use it to represent numbers. Okay. All right, cool. Now, this is using the sign and magnitude representation. There are other ones out there, okay? I'm not saying that Solidity is using this, okay? But this is the simplest to illustrate. There are more ways to represent numbers. There's 1's complement and 2's complement. I know how to do these until I forgot, right? So I learned these in computer science, but I haven't used it in such a long time that I don't remember. But those are like way more complicated than this. But this sign and magnitude representation, it shows you the principles of like how things kind of work. So that's like more than sufficient, all right? Okay, any other questions? Those are some good questions. No more questions so far, okay. So I'm going to skip mapping for now. I want to do it in person. Okay, so let's skip over to functions first. Okay, because if you've been looking at the slides, you'll see that we're doing mappings afterwards, but we're doing functions, all right?
Professor?
Yeah.
What exactly is underflowing again?
Underflowing happens when you, okay. So let me draw it out, right? So let's say you have a number range, 0, 1, 2, 3, okay? These, you can only represent those 4 numbers, no more, okay? 4 numbers is like, because you have a goldfish brain, so you can only deal with 4 numbers, okay? So an overflow happens when, let's say, right now the number's 3, but if I do 3 plus 1, what's going to happen? If we have a normal brain, then we'll say 4, but we have a goldfish brain, we can only handle those 4 numbers. So imagine this is on some kind of coordinate system, all right? So let's say we have like different marks on it, okay? So overflow, so when you're adding a number, you just move the marker to the right side by 1, right? But there's nothing past 3. So what we do is our goldfish brain just wraps it around, right? Back to 0. Okay, so 3 plus 1 in this number system just returns to 0. And then 0 minus 1 in this case goes back to 3 because we're goldfish brain, right? There's no negative numbers. We can only handle these 4 numbers, right? So this is like a good way of thinking about it. It just wraps around. That's overflow, underflow. Yeah.
Yeah, thank you.
Mm-hmm. So one way to check overflow is if you're adding 2 numbers together, if the sum that you're getting is smaller than either number, then you know it's an underflow. Oh, sorry, you know it's an overflow. If you're subtracting 2 numbers and the result that you get is bigger than both, then you know it's an underflow. Okay. Before Solidity version 0.8, you had to explicitly check for those. But in the newer versions, they will check it for you, so you don't have to worry about it. Okay, but still helps to know that like what they are, because a lot of the smart contract bugs stem from programmers failing to check overflow and underflows. Imagine if you have like a balance thing. Okay, if you have a if your smart contract keep track of like the balance of different people's bank accounts, right? And if someone overdrafts, what you're supposed to do is actually stop them from overdrafting, from getting the balance into negatives. But if you don't check for underflow, then what happens is that person will become the richest person in the world because the balance wrapped around to the largest number. Okay. So that's like some problems that they can cause, all right? Or the richest person can become the poorest person by wrapping around the other end, right? Okay. So we're skipping mappings. Again, I'm going to do that in person. So let's move on to functions. Okay. So a function is a reusable collection of related but smaller actions. Okay. So think of starting your car as a function. Okay. So what happens when you start your car, right? What you do is you walk to your car, okay? You pull the door handle, you have one of those keyless entry stuff, right? You get into the driver's seat, you shut the door, put on the brake pedal, push the button, and then your car started, okay? But we, as human beings, but if you look at starting your car in this way, they're really a bunch of discrete and smaller actions, right? But whenever you tell someone to go start their car, you don't tell them to first walk to your car, then pull the door handle, then you don't say that. You just tell them go start your car, right? So this is like our human brains kind of like we're already actually very familiar with the concept of a function, right? But the function really is just it's putting this thing that we've been using into a formal definition. Okay, so again, it's a reusable collection of related but smaller actions. Okay. So what functions can do is that functions in code, they can manipulate, they can modify variables, and they can also call other functions. Okay. I'm actually not going to go into this right now either. I just want to prime you guys, kind of talk about in general what a function is, and some of these stuff I'll talk about when I'm in person next time. Okay. So these I'm not going to talk about. Okay. For now, I just want to take some questions on what we've gone over so far when we talked about variables. Anything you want me to repeat? Any confusion? We could talk about it. Let's see. Can I go over to 27 in binary? Yes, I can. So let me add a new slide. Cool. Okay. So 27. Okay. 27 in binary. Okay. The first job that when you're trying to convert a decimal into a binary is to find an exponent of 2 that would get you over 27, but not under 27. Okay, just over, right? So 2 to the third is 8, 2 to the fourth is 16, still under 27. 2 to the fifth is 32. So that's the one we're looking for, because if we go one under 2 to the fourth, then we go to 16, which is smaller than 27, right? So we actually start, or you can start from 1 under, whatever, but this is how I like to think. So we first find 1 over. So 2 to the fifth is 32. And 32 we're not going to use, but we want to start from there, okay? And then we just write out 2 to the fourth, and we keep writing until 2 to the 0th, okay? 2 to the third, holy shit, that is horrible. 2 to the second, it's getting worse. 2 to the first, oh, this is a nice one. 2 to the 0. Okay, Richard, I'll explain it in a bit. Right, 2 to the fifth, 32, okay? Actually, I'm not going to write out the values, it's too painful. So 32, we're not going to have anything to do with 27, so it's a 0, okay? Because it's bigger than 27. 2 to the fourth is 16, okay? So we can make use of that. So we subtract 16 and we put 1 here. The remainder is 11, all right? 2 to the third is 8. 8 is smaller than 11. So we can do 8 here and mark 1, okay? And that equals 3, okay? 2 to the second is 4. 4 is larger than 3, so we can't use that, 0. 2 to the first equals 2, all right? 2 is smaller than 3, so we can use that, okay? And now we're left with 1, which is exactly 2 to the 0th, right? So 1, so now we have no remainder, and we're done, okay? So 1, 1, 0, 1, 1 is 27 in binary form. We can do another number if you want me to, just not too big. Oh, no, the three value thing, I was just picking like a 3-bit system so that like, no. So that was only for that one example. I'm saying we're only allowed 3 values. Okay. If it's a UNT256, then we're allowed 256 bits, right?
Could you do the
Okay.
example with like say 19? Sorry, just so I can, because I'm trying to understand if some
19?
numbers. Yeah, if some numbers can't be covered somehow.
Okay. Do you just want to do 19, or do you want also, we can also do a bigger number. There's more math if you want to. That's fine.
Yeah, I guess I'm still just trying to understand like if there are some numbers that we wouldn't be able to get into binary because you can't do it with this system, or can you do infinitely?
Okay, what's your birthday?
January 19th, 2002.
January 9th. Oh, January 19th.
Yes.
Okay, so let's do 119. How about that? Let's convert 119 into binary. So let me select these. Can I copy them? Nope, I can't. I'm just going to move this down so I don't have to rewrite all that stuff. Okay. So 119. So 2 to the 5th is 32. Okay, that's smaller. 2 to the 6th, 64, still smaller than 119. 2 to the 7th, 128. Now that's bigger, so we can start from here. So this will be 0 for sure. Okay, because we can't have the point is to find to look for a 2 to the whatever power that's just big enough for this to have the smallest remainder, and then to keep going. Okay, so 2 to the 6 is 64. Okay, so we can mark 1 here, and we subtract this by 64. So what's 119 minus 64? It's 55, right? I need someone to check this. I think it is. Right? And then 55, okay, so that was 64. Here, 2 to the 5th, 32. We can do that, right? So that equals 23, right? If you see me doing math wrong, just tell me. Okay. 2 to the 4th, 16. Okay, you can still do that. That equals 7. Okay. 2 to the 3rd is 8. We can't use it because 8 is larger than 7. We're going to have a negative remainder. So that's not going to happen. Okay. 2 to the 2nd is 4. We can do that. All right. Equals 3. And then 3, 2 to the 2nd is 2, and then 2 to the 1st is 0. So that's like 1 and 1 here. Okay. So every number you're trying to represent is the difference between not squares of 2, powers of 2. Okay, square is just 2 to the 2nd or something to the 2nd. Okay.
And why was 2 to the 5th assigned 1 again? Sorry.
Because okay, so 64 is 2 to the 6th, right? And 119 minus 64, we got 55. Because 2 to the 5th is 32, which is smaller than the remainder, right? But it's so we can subtract it and then mark 1 here.
Gotcha.
It can't be larger than the remainder. If it's smaller, it's fine. So this is why we skipped 2 to the 3rd, 8, because 7 minus 8 will be -1, and we can't have a negative remainder. So we skipped 2 to the 3rd. We're like unintentionally getting this weird pattern where we have a 0 in the middle and a 1 in between and 1 everywhere else. The biggest number of UNT56. Yeah, I think the matrix is real. Okay. The biggest number of UNT56 is that. Then what is the biggest number of int56? Okay, so we can and also is this clear to is this like the binary thing? Are we okay? You can try more on your own. Just come up with random numbers and do them. There won't be a case where you can't, like, it's never going to happen where you have some remainder that you can't take care of. All right. So let me move on to, okay, so Joe said, the biggest number is UNT56. Okay. Let's look at this case. Okay. So this is a UNT3 and an int3. Okay. The largest number of an int3 is 2 to the third minus 1, 7. Okay. The largest number of, sorry, that was in UNT3. So the largest number of an int3 is a 3. What is a 3? It's 2 to the second minus 1. Okay. So, so the biggest number of int256 is 2 to the 255th minus 1, because you're missing one bit and using it for the sign. All right. Okay. Is that a confident okay or okay? I can't tell. All right. Can I explain again? Okay. So observe. This is a UNT3. Okay. Largest number, 2 to the third minus 1. So in an UINT, the largest number is 2 to the number of bits minus 1. Okay. In an int system, because we're taking one bit away to represent the sign, then the largest number will be 2 to the bit number minus 1 and then minus 1. Okay, so if I type it out, it looks like this. Oh, geez, sorry. It should look like that. Okay, so what I typed here in the chat is the largest number of an int whatever number of bits. Okay, so if it's an int3 like we have on this slide here, then 2 to the 3 minus 1 minus 1, right? So that's 2 to the second minus 1. That's 4 minus 1. That's 3. And as we can see here, it indeed is the largest number that we can represent with it. Okay. Okay. Did you? Okay. You just copy and pasted it. Okay. Oh, I didn't know you could delete. That's a new thing. All right. Okay. Do we have any other questions? Anything goes.
What is a byte 30? Can you go over byte 32 again?
Oh, that's right. I'm sorry. A byte 32, it just represents like a 32 byte piece of data. It could be anything. Like you can convert a UNT256 into a byte 32. Like a byte, like a byte type is like the most generic type ever. You can convert other types into it, and you can convert it into other types if applicable, if it's valid. Okay. It just means that it's a type that holds 32 bits of whatever data. And usually it's in the form of like a 32-bit number. Sorry, 32-byte number, which is a UNT256, really. But then you can also use it to represent a string that's smaller than 32 bytes. And usually if we're talking about alphanumeric strings, so the English alphabet plus all the numbers and whatnot, each character is usually 1 byte. So that's why you can represent 31 or 32 bytes, depending on some of the implementations of stuff. It's a bit different, but it's either 31 or 32 bytes, or sorry, 31 or 32 character long word.
So how is that different than a string?
A string can go over 32. A string doesn't have an upper limit.
Okay.
But the string is more expensive. Remember the well analogy I used. If every bucket can only contain 32 bytes, and when you're retrieving a string, there's a chance that you'll need multiple up and down round trips of the bucket to retrieve everything. So that's more expensive. But for bytes 32, it's one storage slot exactly. So it's a single retrieve.
So it's like a string. Is a string made up of bytes 32 then?
String is made up of individual bytes. And it also has another, a string is a more complex type, meaning that it's made up of other basic types. Okay, so a string is basically like a bytes array that we say. So an array meaning a list of things. So it's a list of bytes that can go on for, that could be infinitely long as you don't blow the gas limit trying to save it, trying to store it. But a string is basically a bytes array that also stores how long this thing is. So it's more complicated than the bytes 32 or bytes anything. So you can have a byte to bytes 2, bytes 3, 4, all the way to bytes 32. So you can have these as like, when you have it as these types, then you know exactly what the length is. But with a string, it's more dynamic. So it gives you flexibility in terms of storing. Like if you don't know what's the length of the data that you're going to store, you can use a string. But just remember, storing things on the blockchain is very expensive. And also things that are usually useful for identifying information, such as hashes or whatever, fits nicely into a bytes 32.
Okay, thank you.
Yeah, and it'll make more sense when you start writing stuff. All right. Any other questions? Last call. When would we use ITP-356 versus uint? When you need to represent negative numbers. But usually you don't have negative numbers in Solidity. Like usually we don't use negative numbers. But if you need to use negative numbers, like if you're keeping score of a game and someone can go negative, then you can use an int instead of a uint. But usually people just go for uint because usually we deal with like money transfers, token transfers, or whatever, or number of items or something. And these usually don't go negative, right? There's no such thing as like a negative inventory. Just can't happen. You can't sell what's not there. And there's no such thing as I'm like no one's ever said to you, let me give you negative $100, right? So in most cases, we don't use int, and usually you don't see int being used because there's like the use case doesn't involve negative numbers. Right. All right. Do we have any other question? If we don't, I will end the class a bit early today. Thank you for coming. I will be back on Thursday in person. Hope you have a good rest of the day.
Thank you.
Bye, everyone.
Thank you.
Thank you.
Thank you.